All right, so yesterday we spent the first half of class balancing. We're going to continue with balancing practice because, again, your Unit 5 quiz is going to ask you to balance reactions. And don't forget, balancing is more than just obeying the law of conservation of mass. It also is all about revealing really important ratios between the molecules that react together. Those ratios are eventually going to lead us into predicting and quantifying the amount of each chemical species we either produce or need, okay? So this is a very critical original skill set, all right, that we need to confirm that you guys understand. So we then closed up the second half of class in the last period with a discussion on 3 out of the 6 types of chemical reactions I'm going to introduce, or 3 out of the 5 with a 6th bonus, kind of weird one. So in your workbook, when I have you guys write type, what I mean by type is I want you to give me the category of what reaction type it is, okay? So a lot of you guys could only have done maybe 1 in the practice book because you didn't learn the rest of the types yet, right? But what we have here is, okay, we have our warm-up. We have a hydrocarbon. Reacting with pure oxygen to produce carbon dioxide gas and water gas. Okay, so we would categorize this as a combustion reaction. Okay, so technically there's also a ton of heat being released as a product. Heat delta. All right, for your quiz on Monday, or for 2023, on Monday, I'm only going to give you the reactants. You have to be able to predict based off the reactants what the product is and then balance. Okay, so keep that in mind. So for balancing, can anyone tell me what the coefficients they got were before we balance, like before I show you the process? Min? Yeah, just the numbers, just list them off for me.
1, 10, 3, and 4.
1, 10, 3, and 4. Okay, let's see if that's right. So, I have 3 carbons and 8 hydrogens. I'm going to list what I start off with unbalanced. Unbalanced. I'm going to list what I start off with. Okay, and just to make it clear for right now, I'm going to erase that. And they're bonded together in the hydrocarbon, and then I have 2 oxygens. That's what I start off with. I end with 1 carbon, 2 oxygens attached to that carbon, 2 hydrogens, and 1 oxygen attached to that hydrogen. So what I do is I first deal with my carbons because I'm going to generally save my H's and O's for last, okay? You'll find that sometimes that doesn't always hold true, but for the most part, that's a good place to start, is not your H's and O's. Okay, so I'm going to multiply my product carbon by 3. And because it's attached to that 1 subcategory of oxygens, okay, I'm going to multiply that by 3 as well to get me 6. So I have carbon 3 total on the product side, oxygen 6 plus 1, which is 7 on the product side, and 2 hydrogens on the product side. So what do I look now? Okay, my O's are clearly messed up. Gonna deal with that later. Let's deal with the hydrogens. Okay, I'm gonna switch to different colors. Next step, my hydrogen is 8 on reactant, but I only have 2 on the product. So I'm gonna multiply my hydrogen by 4. But if I multiply my hydrogen by 4, Drea, if I multiply my hydrogen by 4, I have to multiply my oxygen that's attached to it by 4. So I get 8 and 4. Now I have a total of 12 oxygens. Damn, I can't count. Oh, I can't count. So, what I have is 10 total oxygen now on the product side. So what am I going to do? Well, what's really nice is on my reactant side, I have an unattached oxygen. So I can just simply multiply that oxygen, that diatomic oxygen on the reactant side by 5 to get me my 10. Okay, so what do I get then as my coefficients? I get 1, excellent, but I'm not going to write that because that's stupid. I'm going to get 5, Okay, I'm gonna get 3 and I'm gonna get 4 because it's okay. Because I take whatever I multiply by and that becomes my coefficient. Once I write the equation, do I mess with the subscripts when I balance? No. If you mess with your subscripts when you're balancing, you need to stop. You need to say no. Okay. So how would I say this out loud? What does this translate to? This tells me in this chemical reaction. Does anyone want to try to translate this, Aislinn? You could call it, the technical term is actually butane. Butane. Oh, wait. Propane. No, it might be propane. It's propane. Go for it. That's the common day term. You could also say tricarbon octahydride if you want to use your naming skills, but the common term is propane. You're right. Okay, continue on.
So tricarbon octahydride.
Mm-hmm.
So one of those plus 5 pure oxygens.
Uh-huh.
Produces?
Yes.
Yes. 3 carbon dioxide and 4 water.
Excellent. All in the gas state. So that's what it translates to. 1 propane or tricarbon octahydride molecule, covalent molecule, non-polar covalent molecule, okay, reacts with 5 pure diatomic oxygen molecules in the gas state to produce, okay, 3 carbon dioxide gas molecules and 4 water gas molecules. That's what it translates to. That's what it means. So let's do the next one. Everyone feeling pretty good about this actually, like you seeing the connections, okay? Also, you should be seeing the ratio. If you were not drawing on your hand, you might understand it better. Okay, so would you like to somebody share their coefficients, what they have, just to see if we have just a vision of where we're going? Does anyone have this one? 4, 11, 2, and 8 is what we have. 4, 11, 2, and 8. Drea, would you like to explain how you figured that out? No? Okay. I'm going to call on you in a little bit to tell me what the whole sentence means, just like what I did above. So be prepared for that. Hi.
So he does not need comment.
Okay, so for this one, let's see if those coefficients are correct. Let's see if we actually get those multiples. Okay, iron. I got 1 of them, and it's connected to 2 sulfurs. And I got 2 oxygens originally, unbalanced. Not looking at the orange right now. Then I end with iron 2, oxygen 3. What's the charge of this iron? If I needed 2 irons to cancel out 3 oxygen, what's the charge of this transition metal iron? +3. That little 2 only tells you the amount of atoms. It doesn't tell you the charge. The charge you have to figure out by canceling out the sum. So if I have 3, okay, charge of 3, and I have 2 of them, that gets me a +6. And if I have an oxygen with a 2 minus charge times 3 of them, that gets me a -6. That's how I built that ionic compound. Just a quick little friendly reminder. You're gonna want to remember your charges. Okay, so, and then I have sulfur attached to 2 oxygens. Okay, so again, we have oxygen split. Oxygen is a common atom to be sourced in 2 different molecules because it's just so common. Okay, it's just so crucial. So what we do is I'm going to deal with my oxygens last. I'm going to fix my iron. So I multiply by 2, multiply by 2 on the reactant side. So I get 2 irons. Nice. And now 4 sulfurs. Oh, okay. Now I'm going to deal with my sulfurs. All right, new problem. So I'm going to multiply my sulfur by 4. And because it's attached to on the product side to another oxygen, I now have 4 and 8. Okay. Then I look at my oxygens, and right now I have a total, I have a total oxygen count of 11. Ooh, awkward taco. But here's the plus side. Oxygen 2 is by itself. So what I can do is I can say, well, times 11 halves gives me 11. And if you're like, wait a second, what? Hold on. Let me show you. So right now I'm balanced at the 11 and a half. When I multiply by 11 halves, right now I have 11 halves, 2, 1, and 4. But I can't have half a molecule. But the ratio is true. Like the ratio, the relationship is the same. But since I can't have half a molecule, in order to keep the ratio true, I'm just going to multiply all of my coefficients by 2 to keep the ratio. If I just change this to 11, now I have 2, 11, 1, and 4. That's not the same ratio. I need to keep the relationship between the molecules true. So now I become 4, 11, 2, and 8. And that is my simplest whole number ratio between the molecules. So Drea, how would I say this? What's my sentence of how to describe what the reaction is telling me? Start with counting the molecules. 4, what? React with what? Tell me. Yes, you do. 4, you can count, right? You can read numbers, right? Okay, that's perfect. So let's start there. Okay, 4. What's that first molecule? 4. It's okay, I can zoom in. Okay, what is Fe? What's the symbol for Fe? What element is that? Do you have a periodic table? I think I gave you one at the beginning of the year. It's at home? Okay. Do you have your iPad? Could someone lend their periodic table to Drea? Drea, we will wait for you. Because you are capable of doing this? Yes, you are. You passed my class last term. You can pass it again. Okay. Okay, 4 iron. What's the whole molecule? It's connected to what's that second atom? Sulfur. So when they're in a bond together, so what's the molecule called? Iron. I'd like to make a bond with you. Iron sol. I'd like to make a bond with you. Iron sol. It's not sulfur by itself, though. It's sulfur in a bond. So my clue is IDE. I'd like to make a bond with you. What do you do to the last part of it? Iron sol. You don't know? We can figure this out. So we figured it out. What does this translate to? This is like saying I have 4 iron sulfides that react with 11 pure oxygen gas molecules, okay, to produce 2 iron with a charge of 3 oxide and 8 sulfur dioxide covalent molecules, because it's a non-metal plus a non-metal. So I got to use my Greek prefixes. I just have to tell you how many of them there are, right? Okay, I am trying to help you for the quiz on Monday. So, does that make sense how we all got that? No? Should we go through it again? Okay, so remember, on the quiz Monday, I would give you a much easier problem, but I'll only give you the reactants. You'd have to know what the products are. This is a much harder one, so I wouldn't give you something this hard, but that's the idea, okay? So let's go back to notes. That's our review on balancing. It is your job to practice, okay? Going back to notes, let's talk about the other types of reactions. We're going to skip the rest of page 7 for a second, and we're going to go to page 8. Page 8. Okay? So before we start on this, quickly go over the first 3 reaction types. Go over the first 3 reaction types. Let's do a quick review. Could someone tell me what is combustion? And we kind of went over it, but just like quick review. What is combustion? How would I know what combustion is? Like, what's the clues? And what does it always produce? Could someone tell me that? Yes. Excellent. So for the quiz, Monday, if you see that I give you a hydrocarbon plus pure oxygen, automatically, if I give you a reactant that is a carbon hydrogen based reactant and pure oxygen, boom. What's the type of reaction? Combustion. What are your products? Water. Everyone together, carbon dioxide, water, together. Thank you. Okay, that was actually that was nice. Well done, folks. Okay, and then all you have to do is balance, but your product is not unique. It's like saying it goes through this little machine. If I put all of you in a little machine and you all came out as blue Jolly Ranchers, like no matter what I put in there, it's gonna come out to be a blue Jolly Rancher. Okay, for this reaction type, if you see a hydrocarbon, any type of hydrocarbon with oxygen, carbon dioxide, water, like no creativity whatsoever. All right. So, excellent. We'll do a combustion reaction tomorrow in lab. That's a little, I have to run it because it's pretty, I almost singed off my face last time because I forgot how the flyer comes back at you. So we'll do a different one. How about synthesis? Can someone tell me how they might identify, what is a synthesis reaction and how might they identify it from the reactants? Okay. Synthesis. What could you say? What could you say is a synthesis? Mika? What's a synthesis reaction?
It's two smaller molecules or compounds creating a more complex compound.
Excellent. It's the building of something more complex. So how would I identify this for the quiz? Well, whatever I give you, if this happens to be a pure element, like a pure metal, maybe I'll put it that way. If it's like a pure metal or it's a diatomic, that's a pretty good sign you're working with really simple compounds. And if I combine two simple compounds, I often make a more complex one. Okay, so that's a really good indicator for you on the quiz Monday. If you see a plain metal or a plain non-metal or a diatomic, you're probably actually going to build something more complex because you can't break down a diatomic because it won't break down. It won't break down into two lonely H's. Okay, a metal won't break down further than it is just the metal, right? So that's automatically cancels out the idea of the next reaction type known as decomposition, which is the exact opposite. Okay, this is the exact opposite of synthesis. How would I identify in the quiz that I'm working with a decomposition simply based off of the reactant? Well, one, I only give you one molecule. I only give you one molecule. That's a pretty good indicator. If I only give you one molecule and then an arrow, then I'm going to have you break it down. It's a really good indicator. If I just give you one molecule and then I'm like, good luck predicting, okay? It's probably a really good indicator that I'm going to have you break it apart into its simpler molecules, which often involves a diatomic. It's very common, okay? So for a little example, Eliana, here's an example of a synthesis reaction, okay, that we're going to observe. And actually, maybe I don't need you. Oh, actually, maybe I don't need you. It's good that it's propped. Okay. Sorry. I mean, I need you in my life, but all right. So for this, here's an example of a synthesis reaction. I have magnesium, pure magnesium, simple metal, pure magnesium. Okay. Oh, here you go. Okay. Pure magnesium. And I'm going to mix it with oxygen and a little bit of heat. Okay, so what we get is a reaction between pure magnesium and diatomic oxygen provided by the flame. And what you get, notice, is some white residue. Okay, this is magnesium oxide. This residue is magnesium oxide, Mg oh, ionic compound. That is an ionic compound that I just made by burning magnesium. When we burn anything, we mean react with pure oxygen and a little bit of extra heat. Because oftentimes the flame is the source of the oxygen. Okay. So that's an example of a synthesis reaction. So what does that look like? How would we write it? For example, in the demo, it would be like saying magnesium, pure magnesium solid reacts with pure oxygen gas to produce magnesium oxide, which was a solid. It was a white powder. This is totally unbalanced. This is unbalanced. But that's a good example, okay, of a synthesis reaction. That's what you just saw. Okay. So I'll do the other demo in a second as I introduce the next couple. All right, so that's our 3 that we already covered. Let's cover the last 3, okay? Actually, last 2 and then a half. Yeah. So, everybody got this? We good? Great. No? Did someone say no? Yeah. Okay. So, we're going to skip over page 7 for a second. I'm going to come back to it. Let's go to page 8. So, single displacement reactions are a type of reaction that occurs when one element in an ionic compound is replaced by another element. I call this the affairs of chemistry. It's like when someone dumps you for someone hotter. Okay? Not like that would ever happen, but because you're all beautiful, yada yada yada. So for example, we can have this occur with metals kicking out other metals. Remember, metals are cations in ionic compounds. So what we're really seeing is a switch of cations, a replacement of cations. Oh, a switch of cations. So what we see here is in the example, we have pure magnesium and hydrogen chloride. Those are that's an ionic compound and a free metal. We call it a free metal because it's not bonded to anybody. It's just it. What happens is that hydrogen, which is the cation, gets switched out by the metal. And the metal now serves as the new cation with chlorine. The metal switches places with the hydrogen cation. Okay, so what we see here is magnesium goes from pure solid, no charge magnesium to now magnesium 2+ ion. And we kick out hydrogen. And hydrogen goes from charged hydrogen 1+ to non-charged hydrogen gas. That's what we see happen. So we usually produce, by usually I mean pretty much always, a new ionic compound. Which means that, by the way, when you produce a new ionic compound, you're going to need to check for new subscripts. Because now you have a different charge relationship, right? You have a change in charge. So you're definitely going to want to change, probably actually here, look for subscript change because we're not at balancing yet. We're just talking about making a new compound. So you do need to go through the process of establishing the correct atom ratio before you even think about balancing. You're just trying to build the darn correct molecule. That's where subscripts come in. Now, this replacement doesn't always happen. Not any free metal out there will replace another free metal, or sorry, another metal in an ionic compound. Your reaction only does it if it's worth the hassle. It's like you don't go through the process of breaking up with your current significant other and all the yada yada drama unless that other person is worth it, unless that truly is a better option. The same thing is true with reactions, okay? Elements are not stupid. They're not going to go through the process of bond breaking to form a worse bond, a more unstable bond. That's insanity. Don't do that in your personal life, and definitely don't do it in chemistry, okay? So what we say is we have a reactivity series where we can judge if a replacement is going to occur with a metal. And here's the trick. No reaction occurs when the free metal element is less reactive than the element already in a bond, already bonded. Okay, so for example, okay, calcium and zinc. If I have free zinc, okay, and I have calcium chloride, this reaction would not occur because zinc is less reactive, less desirable than calcium. So the chlorine is not going to go through the entire process of breaking its bond with calcium when it's just going to get right back with calcium. Because calcium's more reactive, more attractive, okay? On the other hand, if I have the example of, let's switch it, calcium is the free metal and zinc chloride. This is totally going to happen because zinc is not that great of a keeper. We're going to replace with calcium. Okay. So this is what can happen with single displacement, and we can have this happen a single replacement with halogens too. With halogens often being anions, the other half of a ionic compound, right? So the halogens will switch places in such a way that you're basically switching out, or here, let me put it this way. Yeah, you're switching out anions, the negative charge in the ionic compound. So just like with metal, there is not going to always happen unless the free halogen is more reactive than the bonded halogen, okay, than the bonded anion. So something to keep in mind when you're trying to identify this, okay, is the reactivity matches Coulombic attraction chains for halogens. Fluorine is the most Coulombic attraction. It's going to be the most reactive. That means if you see fluorine diatomic pure and another, let's do magnesium chloride, you're totally going to see the switch take place because fluorine is going to be the free element that's highly reactive. So it's going to kick out the chlorine. So what we're going to see is that this becomes now magnesium fluoride. That's what happens. This kick out totally occurs. Okay. And here I can kind of write this above. This becomes calcium chloride. Okay. That's the transformation occurs. On the other hand, if you were to do chlorine 2 and magnesium fluoride, this would not occur because fluorine's way better reactivity, way better deal. Won't go through the process of doing all that messy breakup for nothing, unless you're just a glutton for punishment or like a psycho. Okay. So you can force undesirable reactions to occur. It just takes a lot of work and it's really unstable, but it's possible. Just kind of like in life. Doesn't usually work out great in the end, but notice And reminder, all of these halogens are diatomic elements. So when you write them as a free element, please don't forget to write them as a diatomic. Okay. So you have some practice problems below. Try going through. They're a mix of metal single displacement and halogen single displacement. Try telling me if the reaction occurs or not, and then tell me the new compound if it does occur. Go ahead and do this for about a couple minutes. So for this one, okay, silver versus calcium. This is what we call a metal single displacement. I'm going to do SR, single replacement, single displacement. They're analogous to one another. Okay, this one's a metal one. Is silver more or less reactive than calcium? Less. So do we even get a reaction? No, you could throw these things together and nothing would happen. The silver would literally just stay silver. Okay. This one is a halogen single replacement, single displacement. Do we get a reaction? Yes, because fluorine's super reactive. Fluorine's always, if fluorine is a free element, you hands down know something's going to happen. So what we should get then is NaF and Cl2, which means, by the way, this is unbalanced. Why do I only have one F? Because F minus, F takes on, fluorine always takes on a -1 charge. So we got to make sure that our individual subscripts are correct. So we charges cancel. So we have to build a good molecule, okay? And then what we see here is we're not balanced. So we would say 2 and 2 in front to balance it out, okay?
And it would be in that order of the NaF and then the Cl.
Oh, it doesn't matter what order. Yeah. Okay, next one, K versus Cl. K versus Na, the two metals. K versus Na, do we have a reaction occur? Yes, potassium's the most reactive metal out of all of them. So we're going to see that it becomes potassium chloride, +1, -1, and free sodium. And it happens to be balanced. And that sodium no longer has a charge. It just becomes plain sodium. Okay, next one. Okay, this was a metal single displacement. Next one, we have another metal single displacement. Okay, here we have iron versus hydrogen. And the hydrogen is technically not a metal, but it acts like a metal in ionic compounds only. So we see iron versus hydrogen. Ooh, iron is more reactive than hydrogen. So we're definitely going to see a replacement here. And it's going to become hydrogen gas and iron. And I'm going to assume here it's iron 2 chloride because that tends to be more common for us. So we're going to say this is a 2+ and this is a 1-. So that means I'm going to have to balance this out at some point with a 2 in front. Okay. Okay. So next one, we're definitely going to have a reaction. Free element fluorine, that's the most reactive free element out there. This is a halogen, single replacement. So we're going to get the new compound, calcium fluoride. But calcium is a 2+ charge. Fluorine's a 1-. So we're going to need to make sure our subscripts match up so that they cancel out the charges. And we're going to get chlorine 2. Okay, what about bromine versus chlorine? Oh, that's a no reaction because bromine is less reactive than chlorine. So that bromine gas will just kind of float around that calcium chloride. All right, now let's amp it up one. Double displacement reactions are when both ions are being switched. Have you guys remember that live TV series when you do like wife swap? And you get 2 couples to switch out and become new couples? That's the same here, okay? So double displacements reactions occur when 2 ionic compounds switch ion partners. So, for example, okay? And you're going to do a lab on this and see this in a little bit, what I'm talking about. It's very theoretical right now. For example, what we see here is the H switches, okay, with the AG, the two cations switch. And then, of course, the anions switch partners. So we could say that the Cl switches with NO2. You could look at it both ways. You could look at it two ways. I don't really care how you look at it, but what you got to recognize is you switched partners. Okay. It wasn't one single element coming along and taking the spot. It was a full on, I like your partner better. Oh, cool. I like yours better too. So let's make a deal. Let's switch out. Let's switch them out. Okay. There used to be this really creepy, like well, it's kind of an R-rated movie. It's like a horror film thriller about these husbands that went and switched out their wives for bionic wives. They created like, yeah, it was super creepy. And my brother made me watch it when I was 12 and I still have nightmares. So anyway, but it's kind of like that idea. It's like a creepy, like this is better. We're just going to assume that this works. Okay. So what happens is what we get is we get two new ionic compounds. Which means, by the way, if you're making two new compounds, what are you going to have to check for? Check for correct subscripts. Which can include knowing your polyatomics. Check that your new charges cancel. Just because you switch partners doesn't mean you do everything the same with the new partner. It means that you figure out a new, okay, charge relationship. Right? So what happens usually is the first new compound, okay, usually one, okay, new compound is dissolvable in water. We call that aqueous. It's dissolvable in water. The special term is what we say is dissociates in water. The ions split up. So they partner up to only split up again. Okay. But then what happens is then usually the second or one of the two, like one of the two. Okay. I don't know how you want to write that. Other one. Is not dissolvable, okay, in water. What we say is it actually produces a solid compound. We call that a precipitate. What's a really good indicator of a chemical reaction occurring? You get some solid that wasn't there before when you mix two things. So what happens is oftentimes one of those two new compounds ends up being a solid that doesn't split up in the watery solution that you mix them in. Okay. This is where we call an important chart comes in place. Now, I should mention that sometimes both new compounds are dissolvable. Sometimes nobody gets to be a solid. You switch partners for everybody to split up again no matter what. Okay. But there is this really special table known as the solubility rules chart table. All right. That I'm not going to go over yet until we hit the solubility lab. We're going to come back to this for the solubility lab, which is next week. Okay. But nope, don't put anything away. Last minute, go back up to page 7. We have a physical process known as dissociation that is true when is a process, a physical process. Notice there's no chemistry happening here. Is a physical process of ionic compounds splitting into ions when in water. That's what we call an aqueous solution, right? So it's only when in water. I cannot emphasize that enough. It's only when in water. This is when you do not create the precipitate. This is when your ionic compounds switch partners and it still doesn't last. So you all end up breaking up anyway. Okay? Dissociation is not a chemical reaction. It is a physical process that is sometimes part of a chemical reaction like double displacement. Okay? How do you know when I'm talking about a decomposition reaction and not a dissociation? Dissociation always is in water. That's your big clue that it's not, okay, decomposition, and it always produces a charge. Okay, it always produces charged ions. As products. So we'll come back and do a little bit more review of this again before the solubility lab, which is next week, Monday. All right, guys, you should be able to do quite a bit of workbook stuff. Good job.